Hello everyone. Today we are going to discuss about the fifth semester organic chemistry topic. The first one is terpenoids. Before trying to understand what these terpenoids are, how these terpenoids can be classified, and etc., let me give you a simple overview about where these compounds are actually coming from. See, the natural products, the word what you're seeing on the screen right now at the center, the natural products or the chemical substances, the organic compounds which are formed, which are generated by a living organism. Doesn't matter whether the plants or animals or insects or any other microorganism type, etc. Every organism produces its own, like organic substances during its metabolic activities. You know that like when metabolism happen, when you eat food, this gets metabolized and they produce primary and secondary metabolites. So these are the compounds which actually from that process. Okay, so I am just trying to give you an overview what these natural products are. There are different types. So as you are looking at the screen, these natural products can be classified in many types. Not classification types. I'm written here. So we have terpenoids. The first one, that is what we are going to discuss in detail. I have written an example just to make sure that whether you are familiar with these like, compounds or not. Camphor, what we use, during our puja or something like that, that is camphor. Menthol, used in peppermints. Coming to alkaloids, the nicotine is a well-known drug present in coffee and tea. Morphine, narcotic drug, and like steroids like sex hormones, cholesterol, plant pigments which typically contain flavonoid or chromone subparts. Counterparts, and this porphyrin ring system, I'll just show you the picture of porphyrin ring system in the next slide, and prostaglandins, like a lipid family. So these all these compounds are basically from natural products. Now we'll discuss in detail about them. It means not everything. Our primary concern is to talk only about these terpenoids. Okay, then we'll have some more introduction about these natural products. I'm just trying to show you a few examples. Means I've already given the example, but I'll show you a few structures here so that you can get familiar with that. So the descriptions goes like this: the natural products are the compounds which are isolated from different natural sources such as plants, animals, microbes, insects, pathogens, etc. Now these are like secondary metabolites. Okay, these are secondary metabolites. That means they are obtained by the enzymatic reactions of the primary metabolites like carbohydrates, proteins, and vitamins. Okay, because these metabolites, primary metabolites, what I'm talking about, they involve in the direct functioning because they are very much important for the growth and development, the normal growth and development of the body. Whereas these secondary metabolites are just product of their enzymatic reactions. So as you can see, the menthol, the first structure here, which is used in peppermints, which actually gives the cooling effect when you inhale the uh, air. I'm sorry. And here is a nicotine present in caffeine and tea, which is excellent, nervous stimulant. And camphor, as you can see, morphine is a narcotic drug which belongs to alkaloid family, and this is a porphyrin ring system. This is what I said. Porphyrins means, like in larger molecular chlorophyll, um, and the vitamins, etc. We have this system. See, in this case, the magnesium ion is coordinated by the nitrogen macrocycle. This is a macrocycle. Okay, okay. This is called porphyrin ring system, and cholesterol belongs to the steroidal family. Now, what these terpenes actually are? These terpenes and terpenoids, they are not two different words. They are referred to same compounds. But we'll try to understand why initially it is called terpenes and later it turned into terpenoids in the upcoming slides. Now, these terpenoids are a group of naturally occurring compounds. These are not like similar type of compounds. Okay, there are innumerable number of terpenoid molecules over there. These are primarily obtained from the plant source. Sometimes even can be obtained from the other sources like animals or microorganisms, etc. These compounds are highly volatile in nature, and these are the compounds which are responsible for, like the aroma of the flowers or fruits or leaves, or sometimes the bark of the leaves, etc. Okay, they are widely, they are present in higher plants, conifers, citrus, and eucalyptus, as you can clearly see here. Okay, they are present in higher plants and coniferous plants, citrus and eucalyptus plants also. Since they are highly volatile in nature, these oils can be used as an essential oil. And they are having wonderful scent, and they are generally used as a massage oil. Okay, you can see clearly, see I have posted a picture here, different type of essential oils obtained from that particular trees, like sweet orange, lemongrass here, peppermint, and lavender, eucalyptus or tea tree, etc. They are typically obtained from that particular tree. Okay, so here is the word. The description goes like this: the term terpene was first coined because a compound, an volatile compound, volatile compound, turpentine, was first isolated from pine trees. Okay, so since it was the first compound, so obviously the turpentine, it was the name, so they kept the name terpene. Okay, and this terpenes are of different types based on the length of the carbon chain. We can classify them mono, di, sesquiterpenoids, and etc. Only the monoterpenoids and sesquiterpenoids are like chief components of essential oils. That is very important. Only the mono and sesqui. I'll try to explain you what this mono and sesquiterpenoids in the coming slides. I don't want to confuse you at this moment. So only the mono and sesquiterpenoids are the part of these essential oils. They are obtained from the sap and tissues of certain plants and trees. The higher members like di and triterpenoids or tetraterpenoids, etc., they are not volatile in nature. They cannot be easily extracted. They form these tree gums and resins. Okay, these tetraterpenoids are still complex in nature. They are present as vitamins. Okay, like beta carotene ring and all. So that is about the basic introduction of terpenoids. Now, in our syllabus, what we have, let's look at the syllabus itself. The terpenoids, we have to understand what is the definition of terpenoid, what is the isoprene rule which is applicable for these terpenoids, how do we classify them, isolate them, and finally, the structural elucidation of citrol, and synthesis, and the structures of these three components: terpenol, camphor, and menthol. As you can see, I have written the structure here itself. This is camphor and this is menthol. So for the examination purpose, you need to just practice the structures of terpenol, camphor, and menthol. But uh, for citrol, we need to understand how do we synthesize it and come to how do we give the structural elucidation of that molecule. Now we'll talk about the definition of terpenoids. So terpenoids are the hydrocarbons of plant origin of the general formula C5H8N, uh, as well as their oxygenated, hydrogenated, or dehydrogenated derivatives. Now, basically, we'll talk about the C5H8N. That's what looks quite special here, because that means all these terpenoids are like the multiples of the C5H8 unit. If you try to understand what is C5H8N, you can see here them here on the right side here. This becomes the C5H8 family, that means unit, that is also called isoprene unit, like the one you see on the rubber. Rubber is a natural polymer obtained from isoprene unit. I mean isoprene unit gets polymerized. So here we have the same compound. Now, what is this isoprene unit? If we try to understand the IUPAC name of this molecule, this becomes 1, 2, and 3, 4. That means it is a 2-methyl. The second portion is a methyl group here. So it becomes 2-methyl butadiene. Okay, 2-methyl buta 1,3 diene is the correct name of this isoprene unit. Now these isoprene units, they change their number. So that means they are not get polymerized, but at least one isoprene, two isoprene units at least minimum, 3, 4, 5, etc. These forms the terpenoid family. Now, as I said here, there is a word called oxygenated, dehydrogenated, and dehydrogenated derivatives. I'll tell you what exactly those words mean. But let us move on. See, they were called only terpenes earlier, because as you can see, there is a double bond here. So you can see this is alkene, the word called ene. So you say terpene, not an issue. But some of the terpenoids, they contain functional groups like OH group, alcoholic, aldehyde, or ketone functional groups, etc. So since they are oxygenated in nature, that's what the word oxygenated mean. Sometimes So imagine the two terpene units are joined together, but you can so if two terpene units join together, one of the terpene unit, the isoprene unit contain two double bond. If two isoprene units join together, means four double bonds should be there, but sometimes the double bonds won't count as we expected. So that's why it's called dehydrogenated or hydrogenated. Sometimes totally different. So the terpenoids are basically see the multiples of the C5H8 unit. That is the point you need to know. Okay. So earlier they were called only terpenes because they thought there's only double bond, but now they are oxygenated derivatives. That's why it's called terpenoids. Okay. Now these simpler mono and sesquiterpenoids are the chief constituent of essential oils, which are obtained from sap and tissues of certain plants, which I've already told you. So here there's an example. Okay, and in the next slides, I'll show you how to find out the isoprene units in the given molecule. Now we'll see what isoprene rule is. Isoprene rule is very important for terpenoids. In order to understand the structural part of this isoprene terpenoids, we need to understand this isoprene part. Now, what this rule states, see, when all these terpenoids, naturally occurring terpenoid molecules, when they undergo thermal decomposition, they started giving this isoprene unit as one of the final product. So scientists could make out that maybe all these terpenoid molecules are built up by these isoprene units. So that is what is the first finding. Later, another scientist called Ingold, the isoprene finding was first made by Wallach, but in 1925, another scientist called Ingold, he said that all these terpenoid molecules, after analyzing all the structures of the different terpenoid molecules, he came to the conclusion that in terpenoids, the arrangement of the isoprene units are not simply in any random fashion, but they follow a definite order. He said that the terpenoid, these isoprene units are joined together in head to tail fashion. So that's the second findings. So let us try to understand what exactly he meant to say. Look here, we have an isoprene unit here, that is 2-methyl-butadiene. He said that this branched part can be called as head, and this alkene part here can be called a tail part. Now, how do we arrange this in head to tail fashion? That's why here is an example. We have two isoprene units here. I'll share the isoprene units. See, this is one isoprene unit, 5 carbon, and this is another isoprene unit here. As you can see, okay, I'll write 1, 2, 3, 4 and 5 carbon, 1, 2, 3, 4, and this is a branched 5 carbon. These two are joined together here. What we can say that this is the head part, and here is the branched is head, this is a tail part, and this is tail. So that means the head of the one of the isoprene unit is joined to the tail of the another isoprene unit. So that is what he meant to say. So head to tail fashion. So let us try to understand the same thing using a specific example here. We have gerniol and nerol, which are isoprene, means isomers to each other. They are the cis trans isomers. So how do we understand here? See, here is the first isoprene unit. We have head. The same molecule can be arranged like this. See, this is the first isoprene. This much. Sorry. This one isoprene unit, and here is a head part and second isoprene unit. So these two are joined together here. So what is the advantage of this one? Like just by knowing this particular part, that means divisibility of isoprene units in head to tail fashion, we can use this for the structural elucidation of some of the molecules. That is the advantage. You can extend the same thing to nerol also. These two are isomers, one and the same, except the fact that this is like trans and this is one cis in nature. The isoprene rule, what we discussed in the last slide, is not universally acceptable. That means it is not applicable to all the terpenoid molecules available over there. There are too many exceptions. Sometimes the carbon atoms may not be multiples of 5. Sometimes you may not see the head to tail fashion arrangement, etc. And sometimes, the isoprene units may be not exactly, you can find the head and tail part. Okay, there are too many exceptions over there. But I would like to represent these exceptions with two examples here. The first example, what I've taken, is called krypton here. Okay, it's 4 isopropyl. Okay, this is 1, 2, 3, 4 isopropyl cyclohexene on compound. Krypton is also called simply. It contains 9 carbon atoms instead of 10, but this is kept under terpenoid family. This is a terpenoid, but it does not contain 10 carbon atoms. So it violates the rule that we must have C5H8 multiples units. Another example here, carotene. So this is a type of like a tetraterpenoid molecule, very bulky molecules and all. The one you can see in vitamin A type of molecule. In this case, what has happened? If you carefully observe this molecule, here there is an head, let us say head, and here there is a head. So you can say that these two components are joined together in head to tail fashion. Fine, that's perfectly okay. But if you see here, see, this is a head and this is a tail part, and here is a head, and here it is tail part. So now it has connected in a tail to tail fashion here. Okay, here is head, tail, and tail to tail fashion. So these are few examples that this isoprene rule cannot be considered as the perfect rule over there, and it is not applicable to most of the molecules. Okay. Now we'll move on to classification of terpenoids. How do we classify them? We know that all these terpenoids contain the basic unit called C5H8N. Based on the number of these isoprene units, we can classify them. Okay, so as you can clearly see on the table, if the value of N, that is very important here, if the value of N is 2, then obviously the number of carbon will become 10. Okay, because in this case, if N is equal to 2, 5 2s are 10, you get 10 carbon atoms. Okay, they are called monoterpenoids. So as I told you earlier, this is our unit, don't forget. If two of types of these units join together, it becomes C10H16. But clearly, just try to know one thing in your mind, that this carbon and hydrogen ratio may vary. Okay, may vary. Sometimes we have some exceptions. So if it is 3, then you'll get 15 carbon atom species. That is 3 isoprene units joined together called sesqui terpenoids. It's pronounced as sesqui. And if it is 4, then you will get 20 carbon atom species, that is 4 isoprene units joined together called diterpenoids. Now the remaining there is sesquiterpenoids, troterpenoids, tetraterpenoids, or poly. These are quite complex in nature, but we are not even going to discuss about it since it is beyond the scope of our syllabus. Okay. Once again, these monoterpenoids and sesquiterpenoids and diterpenoids, what we intend to study, are further classified based on the structure of the molecule. Uh, as you can clearly see here, they can be classified further into acyclic, that means which are having no rings, there is open chain structures, or contain 1 ring, 2 rings, 3 and 4 rings. I am just omitting tricyclic and tetracyclic ring here. I have not put any example for that. So let us go one by one. So as I said, each class can be further divided. That means mono can be and sesqui and di. All these can be further divided into acyclic, mono, and monocyclic and bicyclic, depending on whether they contain, whether they open chain, contain single ring or bicyclic ring. So let us take a few examples and try to understand what exactly I mean to say. Monoterpenoids, that means it contains 2 isoprene units. In that, we need to talk about acyclic. That means these 3 contains no ring, cyclic ring system. They are all open chain structure. Now, as you can see, there are 2. These are called monoterpenoids because they contain 2 isoprene units. I am going to write them here. Write the number 1, 2, 3 here, 4, 5, 6, 7, 8, 9, 10. You see, all of them, they contain 10 carbon atoms. And they contain 2 isoprene units. I would like to show you that. In this second example, citral, I'll show you how we can write the isoprene units. See, this is the head part, tail part. So 5 carbon atoms. Again here, 5 carbon atoms. These 2 are joined together by a bond. So they are called monoterpenoids. So you can clearly see that in some of the examples, as I said, they are oxygenated derivative. Here it is an alcoholic functional group. Here there's no aldehyde functional group, but they are not cyclic in nature. Now let us move on. We'll see monocyclic monoterpenoids, where we have a cyclic ring here. Where we have a cyclic ring here. I'm sorry about the message. We have a cyclic ring. So you can clearly see this the structure limonene. Once again, I'll write the number of carbon atoms. I write 1, 2, 3, right? 4, 5, 6, 7, 8, 9, 10 carbon atoms. The only thing is these two here is a joint. Okay. Similarly, this alpha terpineol and menthol, whatever it may be, they all contain same number of carbon atoms and they contain single ring over here. You can clearly see that. Next, we'll move on to bicyclic monoterpenoids. As the name itself is suggesting, that means we contains two cycles, means two cyclic rings here. These are further subdivided into here 6 plus 3, 6 plus 4, and 6 plus 5. Now let us try to understand what this 6 plus 3, 4, and 5 actually means. Now look here, the first example what we have is thujane. If you carefully observe, I'll try to number them in order. I'll start from here just to make you understand. 1, 2, 3, 4, 5, 6. There is a six-membered ring in this molecule, fine. But if you just see this part, see, this becomes a six-membered ring. If I write, fine, this is a six-membered ring. But if you do like this, then it becomes a three-membered ring, right? This is a three-membered ring here. So these are called bicyclic. That means the six-membered can be split into 5 and 3. Now, but instead you say 6 plus 3 here. So you have six-membered ring as well as three-membered ring here totally. So that means these compounds are called bicyclic compounds. Okay. Similarly here, as I can say, I'll write it here. So you start from here 1, 2, 3, 4, 5, 6. There's a six-membered ring, and you can write in different color 3 here. So it means this 1, 2, and 3 forms three-membered cyclopropane ring, and this outer ring forms six-membered cyclohexane ring. So that's why it's called 6 plus 3. Next, we'll move on to 6 plus 4. We have another example called pinene. In this case, I'll write 1, 2, 3, 4, 5, 6 here, or else you can write 1, 2, 3, and 4 here. That means this 1, 2, 3, 1, 2, 3, and 4 forms. Look here, this square, this like this. This is a four-membered ring, whereas this is a six-membered ring. The outer one will be six-membered, and the inner one is four-membered. So it becomes 6 plus 4. And finally, we have 6 plus 5-membered ring. I'll write the same numbering order. Write 1, 2, 3, 4, 5, 6 on the outer side, and here is 5. So that means 1, 2, 3, 4, and 5. The structure of this molecule will be like this. We can write like this actually. This is the correct structure of this molecule. I'm sorry. Okay. If you count outside 1, 2, 3, 4, 5, 6. But if you erase this part, let me show you. If you erase this part, then you'll get 1, 2, 3, 4, this carbon 5. It's a 5-membered ring. So there is both 5-membered as well as 6-membered ring present in that molecule. So similarly, we can write here 1, 2, 3, 4, 5, 6 outside ring, but inside 1, 2, 3, 4, and 5. So here is a 5-membered ring, and here it is a 6-membered ring. Don't confuse with that. Okay. We have sesquiterpenoids. As I said, sesquiterpenoids are those which contain 3 isoprene units. We'll do the same classification method, what we did to monoterpenoids. So in monoterpenoids, we have acyclic, monocyclic, and bicyclic. Similarly, we'll see how it works for sesquiterpenoids. The first example what we have here is for acyclic sesquiterpenoids, we have farnesol. Farnesol, now let us try to understand whether it contains 15 carbon atoms, because sesquiterpenoids means N is equal to 3, so 5 3s are 15. So we'll see if it contains 15 carbon atoms or not. So we can write 1, 2, 3 here, 4, 5, 6, 7, 8, 9th carbon here, 10, 11, 12, 13, 14, and this carbon becomes 15 here. Okay, 14. So it contains 15 carbon atoms, fine. Now we'll see whether this contains 3 isoprene units, and we have to also check whether they are arranged in a isoprene rule, means head to tail fashion. Now I'll try to show you. So this is the head part, 1 isoprene unit. This is the second isoprene unit. This is our third isoprene unit. I'll show you here. Okay, they all contain 5 carbon atoms. Now all these isoprene units are joined here. It's here. Okay, Now that means it contains three isoprene units. That works totally fine. According to this rule, so this is head, this is tail, this is head, this is tail, this is head and tail. So we have head to tail fashion, we have head to tail fashion, we have, so everything is working fine. Okay, the attachment will be head to tail fashion itself. Similarly, you can put the same thing in the Zinze bin also. That's also works. So you can say this is the one isoprene unit here. So I'll change the color just not to make you confused. Okay, well, you can take from any side. This is one isoprene, and here's the second isoprene unit here, and here's the third isoprene unit. Okay, and these are joined. Like you can put here anywhere else, not on both side if you can put. So here also it's fine. So it contains three isoprene units. No, you cannot put here. I'm sorry. This is the wrong time. This head to tail fashion means it has to be here only. Okay, head to tail. So this is head. This is tail. This is head. This is tail. So here it is another attachment here. Okay, so similarly you can try for another molecule. If you do not get anything, you can contact me later on. Try it, write all the structures on your notebook and try to draw the isoprene units all by yourself. Identify them. Okay, now we'll move on to see. I have shown all the structures here. That means it contains no ring, sesquiterpenes with no ring structure, sesquiterpenes with one ring structure, and sesquiterpenes with two rings. Okay, try to write, identify the isoprene units here. Okay, now we'll move on to diterpenoids. Once again, we have diterpenoids means n is equal to 4, then carbon number becomes 20. So what happens when this isoprene, let us first count. Let us see whether we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20 molecules. That's totally fine. We have 20 carbon atoms in this molecule, so that works fine for us. Now let us see whether there is isoprene units are there, 4 isoprene units which are joined together in head to tail fashion. Okay, now we'll see also that just for only for this molecule. So we have head here. Very quickly we'll write this is one isoprene unit, this is a second isoprene unit, this is a second isoprene unit, here is a third, and here is the fourth isoprene unit. Okay, all these units are joined together here, head to tail to head, tail to head, tail to head fashion. Okay, now we have 4 isoprene units, that is diterpenoid. Similarly, you can put the same thing here also for monocyclic diterpenoids, and I have not shown bicyclic diterpenoids here, but actually for our syllabus sesquiterpenes is totally sufficient. But okay, but if I get an example for this bicyclic diterpenes, I'll post it later. Now let us talk about the isolation of these terpenoid molecules. What do you mean by isolation? Isolation means the technique where you are going to, like extract or separate a particular compound which you need from a mixture. So in organic chemistry, we have different type of separation techniques. Out of that, I am showing you here the steam distillation technique. Steam distillation is technique where we can distill some compounds which are quite having affinity with the water molecules. You pass the steam, and like when you pass the steam to this mixture, some of the components actually like get attached with this steam molecule, that is water molecule, and get condensed to form pure compounds. Now let us see how these things are going to happen. As I said in the first slide itself, not all terpenoids are steam volatile in nature, only the mono and sesquiterpenoids. I have already told you that these mono and sesquiterpenoids are quite, like volatile in nature, and that's why they are having that scent, that aroma smell. Now we need to isolate them. So let us imagine that we have taken a leaf, marcinated leaf, that means a soaked up leaf, soaked up in a particular organic liquid. Now what we are doing, we have taken this macerated leaf here, and we are just passing steam. Let us imagine here is a water, and you heat the water, and this steam comes here and mixes here.
What is the basic principle of this steam distillation is the combined vapor pressure becomes equal to the atmospheric vapor pressure, because we know that if any molecule has to get distilled means it has to get boiled. In this case, actually we are not boiling the pure substance. In this case, the water is actually coming down and it is taking all the vapors of this mono sesquiterpenoids and it is going up. So here's the steam coming down, and then this steam takes up the essential oil vapors and it goes up. Now what you're doing in this part, this is called condenser. What happens in condenser, there will be inner inlet and as well as the outer jacket. In the outer jacket, you just allow the cold water to flow. Since the cold water is actually flowing on the outer jacket, these molecules get condensed. Okay, condensed and becomes liquefied. Okay, the hot vapors are rapidly cooled and get liquefied, and here is your product. Okay, this is the simplest technique. So you say steam distillation is the most widely used method. In this method, macerated plant material is steam distilled to get essential oil into distillate. Okay, now that means at this moment you have both water as well as your essential oil in this flask. Okay, this is the first method. So here is the second part of the extraction process, that is called solvent extraction. In the previous slide, we got a mixture of this pure organic essential oils in water. So now we need to extract that essential oils. What the method we are using is called solvent extraction. What is the principle behind this solvent extraction process? See here, it's clearly mentioned, okay? So we are just trying to make use of this relative solubility of a particular compound in in different immiscible liquids. Uh, Let me make it very clear, just to give you a clear idea how things work. Let us say, for example, you have taken sodium chloride and mixed with camphor. And sodium chloride is white, camphor is also white. You just crush them together and you have the compound. Now you want to extract this camphor. You want to separate this camphor from this, what is that, sodium chloride. Then what do? You take this camphor and sodium chloride mixture and you dissolve it in water. Dissolve it in water and take this in this vessel. So now this camphor is insoluble in water, but the sodium chloride is definitely soluble in water. So what happens once you add water, sodium chloride gets solubilized, but the camphor is still there, which is insoluble in nature. To this mixture, let us imagine that you add an organic solvent. From the basic organic chemistry, we know that like dissolves like, the organic compound tend to be more soluble in organic solvents. We have different type of organic solvents in laboratory like chloroform, carbon tetrachloride, diethyl ether, or tetrahydrofuran, pentane, hexane, etc. So based on different polarity. Now let us imagine that we have taken a solvent which is less denser than water. That's why it is floating on the surface. Here there's a clear distinction. Okay, this line. So what happens when you add organic solvent and shake this? You shake this mixture, you close the tap and you shake the mixture for about 20 to 25 seconds. Then what happens? This camphor which is present in water immediately move towards this organic layer. This is a simpler understanding. So what happens once all the camphor enter into organic layer, but your sodium chloride is present in water? You separate them. You just open the tap, you collect this aqueous layer in one beaker, you collect the organic layer in the other beaker, so you have your camphor, pure camphor in organic layer. This is the basic principle. Now what we are doing the same thing here for this molecule. So in the previous slide we have received this distillate, the final distillate. Okay, we have received this compound. So in distillate means we have this essential oils here as well as water and some other impurities. We take that mixture in this water first. Now all the molecules are with the water itself. You add an organic solvent here, you shake them, then essential oil come to this organic layer, because we know that all these terpenoid molecules are organic in nature. They are made up of carbon and hydrogen. They're made up of this hydroxyl group or aldehyde or ketone group. All these are organic compounds. They come here to organic layer. So what is the point here? You need to understand. We have studied Nernst distribution law in the previous class. So what Nernst distribution law says, the distribution coefficient is always stays constant. So what happens, all the molecules will not come to organic layer all at once. So you need to do it portion wise, part wise. So that's why instead of taking 30 ml of organic solvent all at once and shaking, you take 10 ml each time and do it 3 times. then you can easily extract all the available essential oil to the organic layer. So what happens once you extract all the essential oil to the organic compound? You open the tap, you collect this aqueous portion in one beaker, and you collect this organic layer in another beaker. So the aqueous layer contains insoluble impurities or water soluble impurities, etc. Now the organic layer contains only the essential oils. So you take this organic layer and do the distillation under reduced pressure. This instrument, what you're seeing right now, is called rotary evaporator. This instrument does, now what it does, it distills the solvent. Okay, it evaporates the solvent at lower temperature. What is the principle here? This instrument is actually connected to a vacuum pump. This vacuum pump actually sucks the air which is present inside this instrument. Since the air is sucked out, the pressure is now decreased. It is now the atmosphere pressure is not there. So we know from the basic chemistry, if the pressure is low, the boiling point also is decreased, of a liquid decreases. Let us imagine that we have a liquid at boiling at the 100 degrees, 80 degrees Celsius at normal atmosphere pressure, that is 1 atmospheric pressure. If you connect it to vacuum, then it boils at 50 degrees Celsius. If you increase the vacuum, if you increase the sucking power, it we can boil even at still lower temperatures. So what we do, why we are doing this distillation under reduced pressure? Because some of the essential oil may decompose before reaching the boiling point of the solvent. So if you start boiling at 80 degrees Celsius, imagine if the essential oil is decomposing at 70 degrees Celsius, then this doesn't work. So what we are doing steam, means reduced pressure distillation. So within 50 degrees Celsius itself, all the solvent molecules will be evaporated. So you take the mixture here in this vessel. I'll show you once again. I'll just erase all of them, all this. So what is the point here? You collect all the organic layer, you fill the organic layer here. Then this is a water bath. It heats the material, heats the mixture, and the solvent goes up and collects here, get distilled, leaving behind pure essential oil in this flask. So this is how the solvent extraction process work.